Okay, so we're having trouble making this table, and I've just said it's hard to see how we can do the algebra necessary for this course, which is past midterm now, if we don't know this basic rules for exponents. Okay, you have to be able to do them. So I say that by way of just urging you to do that. And hopefully, I'm developing a kind of a remediation set of drills in open math. One of the things I did over break is I learned to write these questions in open math. It's a simple programming language, but like any language, there are bizarre things that happen. I'm able to write the programs, but then if that rhythm keeps up, I'm gonna have to start dancing to it. And I don't know what I'm gonna do. Okay. So we've got to know how to calculate these numbers. If you know how to calculate the numbers, you don't have a clue of what's going on with the function. Now you can do stuff with it. You can do some algebra, you can answer some questions, but you don't really understand. And we really kind of want to work on that. Okay. So again, what's 2 to the negative 2? Is 1 over 2 squared, which is 1/4. 2 to the negative 1 is 1 over 2 to the 1, which is 1/2. You can't calculate this. I can, you can't. Okay. And 2 to the 0 is 1. And you can't calculate 2 to the 1/2. I could say nobody can calculate this exactly, and nobody can calculate this exactly. I can't, you can't, your calculator can't, nothing can calculate it. It cannot be calculated exactly. It's got a value, but nobody can write it out in decimal form, you know, with numbers. Okay, so you can't calculate, and you get as close as you want. Okay. Your calculator probably calculated out the 8 significant figures. Okay, so if 1 is this big, you're as close as the next atom, or very close to that, depending on how many. You probably need 10 significant figures. 9 might be sufficient if 1 is this big. But anyhow, point is, you can calculate very, very close, as closely as you like if you have enough time. But there's never enough time to get it done exactly. That would take an infinite amount of time. And that's an important idea. Okay. Anyhow, then you get 2 to the 1 equals 2, and 2 squared equals 4. And this is something you really should have been waking up every morning and doing it in your head. Okay. Well, not really. But it should be very familiar to you. All there are five of the most basic functions. You'll be able to do the table and graph the things instantly. Otherwise, you don't know deeply enough what you're doing in the course. Okay. And you don't understand the transformations and a lot of stuff that people are still having trouble with. Okay, it's all based on this arithmetic. Okay, so want to make that point. Please get this in your head. And please understand these rules for exponents as they've been explained, okay? It's gonna make you much more likely to be successful. And you're gonna be successful at a higher level. Okay, so we can do the graph. as I've done thousands of times. Put -2 here and 2 here, divide these intervals in half, you get -1 and 1. Divide this in half, you get, well, let's go over here a little further. I went too far the other way, but here's -1/2. And divide the interval from 0 to 1 in half, you get 1/2. And then you're gonna need numbers from 1/4 up to 4. So you divide 4 in half, you get 2. You divide 2 in half, you get 1. You divide that in half, you get 1/2. You divide that in half, you get 1/4. Look like this, and those intervals should be divided in half, not just random points from the graph, accurately sketched. Then at -2, you got 1/4. Okay, well, that's going to be a point here. At -1, you got 1/2. That gives you a point here. At -1/2, you can't calculate it. You can estimate it. Once you get your graph, you could estimate e or 2 to the -1/2 or 2 to the 1/2, but you can't calculate it. Your calculator claims to, but it's not right either. A lot righter than you are, a lot righter than I'll ever be, okay? You take me an afternoon, that probably takes that long to calculate it by hand out of 10 significant figures using the Taylor expansion, but you don't know Taylor expansion, that's second semester calculus. Okay. Okay, so anyhow. You got 0, 1, you got 1, 2, then you got 2, 4. And now you've got an accurate, to the extent that your graph is accurate, mine's got flaws. I'll bet this isn't really above 2. Yeah, kind of screwed it up. Okay. But it's close enough to make reasonable estimates if you need to make reasonable estimates. So this is what your exponential function looks like. Well, you want to be able to draw a reasonable graph because now you have this graph, you can draw any exponential function. You just have to relabel your axes. Okay. Now, here's your basic. Exponential function. General exponential function. Y equals b to the x. What's the difference between y equals b to the x and y equals 2 to the x? Okay, so it's fairly obvious. Difference between this and this is this has a 2 here and this has a b here. Okay, so b is the base. B has to be greater than 0. Okay, because x can be 1/2. Just because you can't calculate it doesn't mean it can't be 1/2. There is a value, right? There it is. There's an approximation to the value. If you use projections here, you're probably going to come out somewhere around 1.4. Right? So I project up here, I project over here, you get something. It pretty much looks like a little less than halfway, 1.4, and that's about what it is. More accurately, it's close to 1.414. And I don't know what comes after 1.414, although you gave me a little time, I can calculate it. Not in my head. I have to actually write things out. And it'll take a little while. Okay, so there is a value when x equals 1/2. Okay. If b was a negative number, well, The 1/2 power is the square root. What's you get when you take the square root of a negative number? You get an imaginary number, not a real number. Okay. Now you can actually graph imaginary numbers, but the graphs are a lot more complicated. Yeah, with functions of complex numbers, okay? And actually the graphs are like 4-dimensional and we can only visualize 3. So, anybody want to do that? I don't think so. I don't even want to do that. Okay, even that, although that was my field in graduate school. It's very complicated. Okay, but very powerful, very interesting. Almost all engineering is built on functions of complex variables, whether the engineers know it or not. And many of them do, okay, at least to some extent. I'm digressing all over the place. My point is, B can't be negative, because if B was negative, you wouldn't be able to do the 1/2 power and get a real number. And not just the 1/2 power, almost any power on the number line, except for the integers. It's the rational numbers, okay? Okay, so B's got to be greater than 0. And there's a reason for it. You really have to carry away. Now, let's do another table. Let's say you got x and you got to do y equals 1/2 to the x. Okay. Now, not to lay the hard things on you right now, because you had trouble with the table, which most of you did. You're probably going to have trouble with what happens when x is a negative value, because you get a complex fraction. So I'm going to start with positive values. Instead of going -2, -1, 1/2, and all that, I'm going to go 2, 1, 0, -1, -2. So you don't get a negative exponent until you get down here. Okay. So make this table. What's 1/2 to the second power? Okay, so we're going to get 1/2 second power equals what? And write it out. Then see what your graph looks like. Okay, well, if y equals 1/2 to the x, then when x equals 2, we have 1/2 squared, right? And most people, when we finally got down to it, were able to tell me that 1/2 squared was 1/4. Okay, if you didn't tell me that, it's because you were kind of wanting to use a negative exponent here and you flip things. But 1/2 squared means (1/2 times 1/2), and that's 1/4. There's the dance again. Okay. 1. X is 1, y equals 1/2 to the 1, of course, that's just 1/2. X equals 0, we have 1/2 to the 0. Well, that's 1. When x equals -1, we have 1/2 to the -1, which is 1 over 1/2 to the 1. And that's what a negative exponent does. Which is 1 over 1/2, which is 1 divided by 1/2, which is 1 times 2 over 1, which is 2. You have to understand all of that. That's what negative exponents do. And then that's what you do when you have a fraction in your denominator. You write it as a division, and you word it and multiply. Okay. And then This gives us 1/4. And I'll let you think about why that is. Now, if we understand these numbers, we can construct a graph. Okay, so I'm going to take these numbers here. We're going to make them. I'm going to plot them. I'm not even going to label these points. Everybody should know what they are. They're the same as they're over here. -2, 4. -1, 2. 0, 1. 1, 1/2. 2, 1/4. And we draw this curve. Okay. It looks just like this curve, but it's been flipped. And why is it flipped? Well, it's because of the way powers of 1/2 are related to the powers of 2. And you can think about the arithmetic here, and you really shouldn't think about it until you understand how this process flips the graph. But the bottom line is B is less than 1 here. Okay, so this is y equals b to the x for b equals 1/2. Your basic exponential function y equals b to the x for b equals 2. Now you'll see we got a question here. Usually means I did something stupid. So let's see what happens. Yeah, that thing about stupid was right. I should have written out the whole calculation. Yeah, this is 4. And of course, that's what I plotted there. I know that, but I didn't write it out carefully. Because I was already thinking about this. No excuse. I was ignorant. Okay, so again, if B is 2, it looks like this. If B is 1/2, it looks like this. What if B was 1? What would the graph look like if B was 1? Look like. And I do need to step out for just a second. I'll be back in less than 2 minutes. What's your graph gonna look like? Yeah, you're getting a pattern there, aren't you?
Yeah.
It's gonna continue. Okay, well, what's 1 to the -2? Write it out. You know, right out the. Y'all didn't do any talking while I was gone, did you? Yeah, well, so we can't identify you. So I can use a recording. I don't know what I recorded and what I didn't. Apparently. Was I recording when I thought I was? Anybody hear the thing say I wasn't? I don't know, there's dead space there. Let's just kind of reiterate. Got the table from 1/2 to the X, people had trouble with it. There are the details, right? 1/2 squared means 1/2 times 1/2, which means 1/4. 1/2 to the 1 is just 1/2. Anything to the 1 is whatever it is. Anything to the 0 is 1. Negative exponents get a little tricky, because 1/2 to the -1 means 1 over 1/2 to the 1. Which is just 1 over 1/2, since 1/2 to the 1 is 1/2. And 1 over 1/2 means 1 divided by 1/2, which is 1 times 2 over 1, which is 2. And then similarly with -2. And here's our graph, y equals b to the x to b equals 1. Okay, just in case I didn't get that down there, that's a quick summary. This shows us that the graph of the b equals 1/2 function is flipped around the y-axis relative to the graph of the b equals 2 function. Okay. Now that's not a general transformation. It doesn't work for other functions. Because what we did here is just unique to the exponential function, which has a base. Other functions are a base to the power. So we want to look at what happens if b equals 1. Now, everybody's making the table, but most people didn't go into the details of calculating these things and wrote down maybe what they thought rather than what it is. Okay, so again, you want to focus on the arithmetic. Okay, so if b equals -2, you get 1 to the -2. What's 1 to the -2? That's 1 divided by 1 squared. Well, 1 squared is 1 times 1. We got 1 over 1. What's that? Yeah. Everybody use this measure. No, yeah, okay. Okay. It's 1, right? Okay. What about 1 to the -1? Well, that's 1 over 1. I'm not going to tempt you to use the wrong thing. I'm just going to tell you what it is. It's 1. Okay. What's 1 to the 0? It's 1. There's a pattern here. Well, 1 to the 1 is 1. 1 is 1 squared is 1. I'm not writing out all the details. If you didn't write out the details and just wrote down what you thought, you missed something obvious, right? So I'm not saying that you're terrible people, and most of you are reasonably okay. Haven't been tempted to, you know, call the cops or the social workers on many of you. So nothing wrong with you, but please pay attention to the details. Don't just write something down because you think it might be true. If you're not paying attention to the details, you're going to miss stuff, and that's going to happen on exams and tests and so forth. And you know that gets you into a situation where you don't make the grade you want to make. Okay. Okay. So what's the graph going to look like? Just quickly show me what that graph would then look like. I did. Okay, so the graph. Well, let's see, here's -2, -1, -1/2, +2, +1, +1/2, 4, 2, 1. And that's actually all we're going to need because all our y values are 1. We're going to get a point here, and a point here, and a point here, and a point here, and a point here. -2, 1, so -2 you get 1, -1, 1, -1 gives you 1. And so forth. We could have even done 1/2. Because 1/2 to the 1 is 1, right? And -1/2 to the 1. We could have done 1/2. 1 to the 1/2 is 1, right? And -1/2 to the 1. -1 to the -1/2, have to write it down to get it right, is still 1. 1 to any power is 1. So all these numbers are going to be 1. We can actually calculate them all. Okay, so you're going to see this graph. Read your text. Without drawing all the details. Here's your graph of b equals 2. Here's your graph of b equals 1/2. Here's your graph for b equals 1. What would the graph look like for b equals 3? Okay, now, from the original graph, and this graph, we have this picture. We have the b equals 1/2, and the b equals 2, and the b equals 1. So there's kind of a pattern that emerges here. So we're going to try to see a little bit about that pattern. Okay, so we're going to do the b equals 3. And if b equals 3, then b to the x is 3 to the x. And 3 to the -2 means, well, right now the details, if you understand the details here, then you'll understand the details there. 3 to the -2 is 1/9. 3 to the 0 is 1 because any number to the 0 is 1. And 3 to the second, of course, that means 3 times 3. And that's 9. Okay. You want to be careful you don't see this as a multiplication. It's 3 raised to a power. Now, if we put 1/9 and 9 on the graph, at -2, we'll get 1/9. So let's just say here's -2. Well, 1/9 is less than 1/4. So that's going to put a point down somewhat below the graph of the b equals 2 function. When x equals 1, of course, you have 1. And if x equals 2, so that would be here, you're going to have 9. So that's going to be way up high. And if you draw the graph carefully, you're going to see that the b equals 3 graph is right here. Now let's if you don't see all that, then you want to make yourself a very accurate graph of this thing. And b equals 2 and b equals 3 graphs are real important because the b equals e graph lies between them. And the graph for b equals e, and I haven't even told you what e is, but the graph for b equals e he's about 2.7. It lies between the B equals 2 and the B equals 3 graph. Okay. That's going to be very important. Actually, it could be argued, and I think a majority of mathematicians might even argue the fact that it's the most important function in the world. Okay, it kind of governs the whole universe. That's an important function, and I'm not going to teach you how to manipulate the universe. You have to take a more advanced course. Everybody wants to learn to manipulate the universe and condense the system. Offer the course, I'll do it over the summer. Not really. Okay. So now you got the B equals 3 graph. The question I want to ask now is, what's the B equals 1/3 graph going to look like? Anybody want to offer an opinion? Now, I would say first, look at the B equals 2 and the B equals 1/2 graph. How are they related? I guess that was worth me recording. Okay. B equals 2 and the B equals 1/2 graph. 1/2 is reciprocal of 2. And you see how that reciprocal changes the values here. If you understand that arithmetic, you understand why this graph is a reflection of this graph. Well, the B equals 1/3 graph is going to be the reflection of the B equals 3 graph. So it's going to something like this. Okay, well, there's a whole series of graphs that you're going to want to understand. The graph that I'm going to have here is in between the B equals 2 and B equals 3 graph. B equals A, B is approximately 2.7. And you don't really need to know that right now, but we're going to talk about it later. You're going to encounter that function very soon. Okay. Start with a function y equals 1.04 to the t. And vertically stretch it by a factor of 1,000. The graph is going to look something like this. Instead of, okay, if t equals 0, what's y? You show me with your finger. 1. If t equals 0, y equals 1 in this case, right? Now, if you vertically stretch by a factor of 1,000, means you multiply it by 1,000. So now y is going to be 1,000 if t equals 0. So just to start out, we have 1, 0, 1,000. That means 0, $1,000. That means you start out, let's say right now with $1,000. Okay. Now you have an exponential function that does something like this. Give it to the right, but I won't want to. That's not what I want to do. I want 18 here. Then I want 36 here. Why did I put 18 there and 36 there? Because of the rule of 72, but I'm talking about that, okay? The value of Y doubles every time T changes by 18. Approximately. So if Y doubles, well, what's it going to be? Y doubles every time T changes by 18. So Y doubles. So here's 1,000. Here's 2,000. Y doubles, so when T equals 18, Y is 2,000. And then it doubles again between 18 and 36. So what's that look like? If it doubles from here to here and then doubles again, can you sketch me the graph? Can you sketch me the point for T equals 36? And copy down this much of the graph. And then what's the value of Y when T equals 36? Okay, now y'all did pretty well with this. Hey, if it doubles between 18 and 36, it's going to go up to 4,000, isn't it? Now, where's 4,000? Well, I didn't leave myself enough room. 4,000 is about here. Well, yeah, okay. I can actually do it. Okay. If I get that right, if I cut 4,000 in half, I'll get 2,000. My 4,000 is still a little bit low, but I don't have any more room up there. So I'm going to plug it. You do that, okay? So I'm going to take one up here. Now, what's my curve look like? Looks something like this. Okay. Now, what this is this is your money. This is your $1,000 after 18 years and after 36 years. Okay. For my age, 18 years doesn't seem like much. It really doesn't. 36 years, I think of things that happened 36 years ago and they seem recent. Okay. So at some point in your life, you're probably going to be glad you left your money in the account to get the interest. You might still be losing because of inflation. That's probably not. That's not been the pattern over the last couple hundred years. We have all kinds of things going on with artificial intelligence now. Who knows what's going to happen to anything? But you make your best guess. So it's important to understand this behavior. Okay, this is like an investment. So, according to your graph, what's your investment going to be worth after 10 years? Can you estimate that from your graph? Probably not going to get a great estimate because you probably don't have a great graph. I certainly don't have a great graph. But if you're careful, you can make a great graph. Okay. What we really want to do is you want to figure out where 10 years is. Okay. So and to estimate the value after 10 years, 18 is here. If you cut that in half, you get 9. So 10's gonna be about here. So according to my graph, there we are. Okay. So I have this vertical line, T equals 10. Intersects the graph here, and the Y value is what? According to my graph, it's probably, I'm estimating a little under 1,400. So I'm going to estimate Y equals 1,370. Now, who has their calculator handy? Okay, so now, we've estimated this value. I've said that at 18 years, the thing ought to be about 2,000, 36 years, it ought to be about 4,000. And there's this thing called rule of 72. You divide 72 by 4, you get 18. Which says this thing ought to double about every 18 years. That's a ballpark rule, but it's pretty close. So if we evaluate this function with the calculator, for T equals 18, we get 2,025. Rule of 72 estimated would be 2,000. Okay. The rule of 72 is pretty, let's see the rule of 72. You read it. Okay. And then, given that, somebody got that in the calculator and said, well, this ought to be about 4,100 because, well, I know how that works. Okay, but anyhow, you got 41, I think it was 4103, something like that. Okay. Then for T equals 10, you got 1,480. Of course, this means that your calculator is broken because I only estimated 1370. Okay. Well, no, and my estimate could have well been 1,400, probably would have been 1,480 based on the way I drew these projection lines. My graph isn't that precise. And your graph won't be that precise. So, well, that's the way it works. Okay, so this is a mathematical model of an investment at 4% annual interest compounded continues. Now, in the public schools in recent years, certainly true, my grandson, when he was a freshman or sophomore, there was a personal finance course. Did you have one? Something about finance and interest and stuff like that. I think, well, you wouldn't have, because you're way younger than I am, but you're old enough that they weren't required that at the time you were in school. Okay. So maybe not everybody would have that in school. Okay. Then, not everybody comes into these classes even had their high school course in Virginia. Okay. So there's a personal finance course. And I don't know what they do in that personal finance course. They sure don't tell you what compound interest is, or if they do, it doesn't stick. Nobody knows anything about compound interest when they come into the courses. Okay. My friends and I all knew about compound interest by the time we were 12 years old. Got that in 6th grade. And then continuous compounding, that was kind of a mystery to us, but we kind of figured it out because, our parents usually had us invest $5 in a bank account to get us started. Okay. $5 was a lot of money in those days. You travel to Europe for $5. Uh, not really. Uh, a small amount. So we start the next. Okay. Uh, and again, sixth grade. Okay. Started compound calculating interest and stuff like that and compounding it. So I don't know what the schools are doing now, but that's a lot more difficult to teach about exponential functions when people haven't ever even thought about compound interest. I mean, that's something you might have, depending on life experience and so forth, but it's not getting done in the school. It isn't getting done. I can't believe there's a course in personal finance and people still come out. And the smartest people come out, it's not being done. And of course, it's not being done because there are a lot of people in that course. This will never come. And not because they're too dumb, because they're not interested enough. And they get away with it. I need to start enforcing some more discipline, penal colonies. That's a good idea. Send people to penal colonies. No. That has its downside. And nobody wants that. Okay. Now the other thing about this functions is this is also the way populations tend to increase if they have enough space and enough food. And don't have predators or once you put predators and disease into the model, it gets more complicated. But the fundamental idea is one of the formative things in my life was my parents' best friends guppy tank. Okay. They had two boys the same age, my brother and I. And we vacationed together, did a lot of stuff. Like they were more like a family. It's my family. When I was growing up. And this guppy tank, about this big, a good sized tank, sitting on a shelf, he stared down the Cheryl's basement. Okay. And guppies are little fish about this long. And you put, a handful of guppies in that tank and come back a month later and the tank will be solid guppies. Okay, they reproduce and they reproduce up to the point where there isn't enough space because they're also cannibalistic. Now the adults don't attack each other, but baby guppies are just food. Okay, so they got to survive. If it gets too crowded, they don't have any room to survive. They don't have any place to hide. Also, you can only put so much food in that tank without that's what the environment. So those guppies probably doubled about every 3 days. Okay. I don't know. I wasn't making estimates at that time, but and they didn't really experiment. The tank was usually pretty much full. So if you start with 10 guppies and they double, what are you going to have? If you don't have enough fingers to use your toes, you tell me 20. Okay. And if that doubles, you got 40, and if that doubles, you got 80, and if that doubles, you got 160. If it doubles 10 times, you've got 10,240 guppies. That tank is full. Well, tank isn't going to get that full. You got a doubling. It just keeps doubling. And you got this exponential function that gets it hugely steep. Okay. So it's like you have exponential function ground. But here's your 10 guppies. Okay. Well, your doubling time is like 3 days. Redraw this. Instead of thinking. Okay, there's maybe what your exponential function looks like. So here. 10 goes. Now you double that, you get 20. So this is how long it took it to double. Here's your time of days. Here's your population. Then you got the 6 days. Then you got 40. Then you got 80. Then you got 160. Okay. And if you do the graph right, the doubling time is always going to be the same. So you got 6. You got 9, 12, and so forth. Okay. And this is a function of the form y equals. N times b to the x. For b is your base. 10 because when t equals 0, you've got 10. When t equals 0, if t is 0, b to 0 is 1, so you're going to get 10, right? You got 10 go through. Okay. We can figure out what b is. Write this down quick. If t equals 3, y equals 20. So I can put 3 in here and 20 in here. And figure out what b is. What equals 10 times b to the third? If I divide both sides by 10, I get b to the third equals 2. So b equals 2 to the 1/3. That might be something like 1.27. Yeah, that's be off by a few hundred there. Okay, so maybe this is. This. All right. Well, that's all we're going to do. So just a summary of what we've done in the support class. First of all, the exponential function, there are 2 fifth functions, y equals 2 to the x. We can even make a table for y equals 2 to the x. Most people in the support class are still having trouble with negative exponents and how to calculate these. And we want to make sure that we're not having a problem. So get that straight if you don't have it straight. I think most people here have it straight either. Because they do it right or they remember, but everything's based on this arithmetic. You want to understand these functions and how they change and so forth. You want to understand it as well if you don't understand the arithmetic, making these tables. Anyhow, we graph the basic exponential function, something we've been doing since the very beginning of the course. One of our 5 toolkit functions, and there's a graph. Now, a general exponential function is a y equals b to the x. The difference between this and this is that instead of 2, we've got b. And b is called the base. And the base has to be greater than 0 because there are a lot of powers that won't work with negative numbers. They like 1/2 power. What's if b was -1, let's say b was -2. What's -2 to the 1/2 power? 1/2 power is the square root. The square root of -1/2 is an imaginary number. You don't get a real number, so you can't graph it, and it doesn't have real values. Now, those imaginary values and complex values are very important, but you don't start learning to do functions of complex numbers until you've had at least 2 years of calculus. Okay, so we're not going to be able to talk about that. Those functions are extremely important. They're the basis for a great deal of physics and engineering. But we don't deal with them. Okay, so for those reasons, we're going to reject negative numbers. And for our purposes, the general exponential function has to be only greater than 0. Now, another demonstration, we can do b equals 1/2 function. Okay. So if b equals 1/2, then y is b to the x, which is 1/2 to the x. It's 1/2 to the x. Well, here's our table. I'm not going to calculate it for you, but people, majority of people in the support class didn't calculate this correctly. Only one person actually calculated it correctly. Okay. And then that person tried to fool me. But you just follow the rules. Now, I started with positive exponents, went to negatives. And people did pretty well with the positive exponents, but the negative exponents through. Okay, so just if x is 2, then 1/2 to the second means 1/2 times 1/2. That's what it means. It's 1/4. I don't know how to multiply fractions. And then for 1 and 0, the numbers are pretty obvious. 1/2 is 0, 1, it's not 0. For -1, 1/2 to the -1 is 1 over 1/2 to the 1. Which is 1 divided by 1/2, which is, or 1 over 1/2, which is 1 divided by 1/2, which is 1 times 2 over 1, and that's 2. And if x is -2, we get 4, not 1/4. I forget who said that. Oh, no, I actually wrote down 1/4 and I wasn't thinking. Okay. Well, then, y equals b to the x, or b equals 1/2. That's y equals 1/2 to the x. If you plot these values on the graph, this is what our graph looks like. And it looks just like this graph, except it's flipped around the y-axis. And if you think about, and you should think about how the numbers work, with reciprocals and so forth, you understand why that happens. And you want to understand why that happens. Okay, so I constructed this graph a little more slowly, but you see that b equals 1/2 graph, and no, there exists a piece of purple chalk in here I can actually write with. Okay. So let's say the b equals 1/2 graph. I'll color this in purple. There's the B equals 1/2 graph and the B equals 2 graph. Goes like here. So there are the two graphs corresponding to these two tables in purple. Then we do the B equals 1 graph. Well, people actually make mistakes in this table. So you got to be very attentive to the details of your calculations. Don't skip things, don't write things down if you haven't done the steps. But if B is 1, then Y of course equals 1 to the X. So if X is -2, what's 1 to the -2? It's 1 over 1 squared, which means 1 over 1 times 1, which means 1 over 1, which is 1. Okay. If X is -1, it means 1 to the -1, which is 1 over 1, which is 1. If X equals 0, it's 1 to the 0, which is 1. And 1 to the 1 is 1, and 1 to the second power is 1. And I didn't write out the details there, but you should convince yourself that this thing is 1 for all these X values. And of course, 1 to any power is 1. If you then graph this, it just gives you a horizontal graph. Now I haven't labeled the graph. Here's -2, -1, -1/2, 1/2, 1, 2, the usual graph. And we get this horizontal line through Y equals 1. Well, we can graph that. Here's our B equals 1 graph. Sorry. It's kind of a pivot here. These graphs, there's our B equals 1 graph. Okay. Then you see, if B is 2, we're here. If B is 1, we're here. If B is 1/2, we're here. When B goes less than 1, your graph starts decreasing. If B is bigger than 1, the graph is increasing. The bigger B is, the faster the graph increases. To understand that at the level of the numbers, understand how the numbers work. And that's a stretch because people come out of public schools where calculators have been overused and they can't do these numbers. And it's a little scary. Because you can't do the numbers, you can't understand it really well. You might do some algebra with it. You might even believe it, but you don't really understand it. Okay, so make sure you understand the numbers as thoroughly as you can at the most basic level, because then you have a strong foundation. And then build on that foundation of the algebra and so forth. Okay. Now, another graph we did was B equals 3. Well, B equals 3 graph, I just put 3 numbers down. Okay. Yeah, 3 to the -2 is 1 over 3 squared, which is 1/9. 3 to the 0 is 1, because everything to the 0. And 3 to the second is 9. So we have 1/9, 1, and 9. If you compare that with the values we have here, we have 1/4, 1, and 4. Okay, so for this one is 1/4, this one is 1/9. So the blue graph for B equals 3 is going to go down underneath the graph, the purple graph for B equals 2. At this point, it's going to go through 0, 1. All these graphs go through 0, 1. Because of course, when X is 0, you're taking 0 power of your base, and it's always going to be 1. Then when X is 2, this thing is 9 instead of 2. I didn't leave myself room. If that's 4 there, 9 is going to be up here. You can see that this blue graph for B equals 3 is heading up toward 9, where the B equals 2 graph only goes up to 4. So here's a B equals 3 graph. Here's the B equals 1/3 graph. And how do I get the B equals 1/3 graph? Well, just as the B equals 1/2 graph is a reflection across the y-axis of the B equals 2 graph. And that's just because of the way reciprocals and powers of reciprocals work. Then the B equals 3 graph will reflect to the B equals 1/3 graph. So we have these symmetric blue graphs for B equals 3 and B equals 1/3. You're going to see graphs of this nature. You're going to be asked to identify graphs of this nature when we get into the assignments. Okay, so we understand that as thoroughly as possible. Now, here's an exercise we did. We do y equals $1,000 times 1.04 to the t. Now, it turns out that that's a model. I mean, it's an accurate model of the value of $1,000 investment at 4% annual interest compounded continuously. And hopefully, you know what compounding is. Hopefully, you then understand what continuous compounding is. Your book will tell you about it. Personal finance course in high school ought to teach you that. At least compounding, it's not continuous compounding. And it doesn't. So I don't know what the purpose of that course is, because it doesn't seem like anybody brings anything out of it. That's, I'm sure people do bring something out of it. Nothing that contributes to their understanding of later mathematics. That would, and the understanding of natural models. Okay. Anyhow, you got this function. This does tell you exactly what you would have in any given t. If you're compounding continuously, punch it in your calculator, and you would need your calculator. You can't do 1.04 for the 1.7 years. Okay, or 1 7/12, whatever you want to do. This function can be understood by starting with y equals 1.04 to the t. Well, y equals 1.04 to the t fits into this scheme. Okay, here's b equals 3, here's b equals 2, here's b equals 1. Now, 1.04 is a lot closer to 1 than it is to 2 or 3, right? So on the scale of this graph, this would be an exponential function that starts out very slowly. So we wouldn't even really necessarily put it on this scale. However, on the scale I've got here, I can actually draw the curve. Now, this function like this, you can recognize that it's the shape of your exponential function. And if you just grab your basic exponential function, take the shape of it, you can do what I've done here. Okay. If t equals 18, this thing will double. And there's this thing called the rule of 72 that you're worried about. 4 goes into 72 18 times, meaning that this function doubles every time t changes by 18. So we start at t equals 0 with $1,000, and of course, if t equals 0, 1.04 to the 0 is 1, and times 1,000 is 1,000. Okay, so when t equals 0, y equals 1,000. So right here we have the 0.015. This means that at t equals 18, we should be at y equals 2,000. Roughly. Okay, that's pretty close. And this rule 72 isn't exact, but it's a pretty good model. Okay. If we go then from 18 to 36, that's another 18 years. The thing will double again. So it's going to go from 2,000 up to 4,000. So you see how we get this exponential curve. Ask people to estimate the value of t equals 10. How do you estimate for t equals 10? Well, here's 18. Half of 18 is 9, and 10 is a little more than 9. So right here is a line that approximates to t equals 10. Line. And that line intersects the graph here. What's the y value? Well, we project this way, and we've done this since the first day. Okay. And we estimated y was 1,370. I'm just thinking about the value that somebody got in a calculator. I think it was correct. They got like 1480. The actual value should be about $1,414. Okay. So this graph came out with a reasonable approximation. So I can just kind of look at this graph and estimate what my value of this investment is going to be at any time for the first 36 years. And if I want to go out to 54 years, well, I just double this up to 8,000. And next thing the graph keeps getting steeper. And there we have it. Okay. Okay, we estimated that value. Now I said, okay, well, let's go ahead and calculate it. Excuse me, calculate it. Okay. I'm not sure about this 1480. But first thing I had at 18 years. Okay, calculator gave $2,025. Well, that's pretty close to the $2,000 I said we would have by the rule of 18. Rule of 18 is approximate, it's not exact. If we double again, well, I kind of know the way things work when they double, so I was pretty sure this is going to end up on 4,100. It's 4,103. And then at t equals 10, I got 1480. I think that should have been 1414. Actually, no, okay. Shouldn't have been, it should have been, I thought closer to 1414. 1480 might well be right. I mean, of course, the calculator did it right every time. So maybe I know what I'm thinking. Anyhow. Well, there we have it. I think it should be more than this, but less than this, I guess, in 1420 or something like that. There it is. Get another model here. I demonstrated something that you're going to need to do next week. So here's another exponential curve. Now I've got a much smaller unit here. The y-intercept is a lot closer to the x-axis than usual. And if this thing keeps doubling in the way it needs to, it's going to look something like this. Now, what's the model? This is like a tank full of little fish, guppies. Okay, put 10 guppies in the tank, and I'm saying every 3 days, and it's probably not quite that quick, but let's say every 3 days, population doubles. Okay. Then after 3 days, you'll be up to 20. After 6 days, you'll be up to 40. After 9 days, you'll be up to double that, which is 80. After 12 days, you'll be up at 160. So you get a graph that looks like this. Now, I didn't give this function, this function isn't totally accurate. But in fact, I estimated at 1.27 amount to the great estimate. But if the thing doubles every 3 days, and if it's equal to 10 when t equals 0, then it's got to be of this y equals 10 times b to the t. Why 10? Because when t equals 0, b to the t is 1, and we get 10. So if we get 10, it's equals 0, we're gonna have 10 here. Now we can take the fact that this doubles every 3 days and say, that, okay, if t equals 3, then y has to equal 20, because it doubles every 3 days. It starts out at 10, and the t equals 3, it's got to be 20. So we go from 0 to 20, between t equals 0 and from 10 to 20. From t equals 0 and t equals 3. Okay, if this is solved, then we can put that y plus 20 here and the t equals 3 here. And we get this equation that we can solve for b. That's an easy equation to solve for b if your algebra is reasonable. Divide both sides by 10, we're going to get 2 equals b to the third. And if b to the third is 2, then b is 2 to the 1/3. And I estimated that to be about 1.27. So that then the model b is 1.27. We just replace b with 1.27. We get y plus 10 times 1.27 raised to the 2 power. Now that's something that you're asked to do actually in the first assignment on exponential functions, which comes next week. So that's very important. As you'll find out when you get your first assignment in exponentials. Now we'll talk more about exponential functions on Thursday. How we want to move to talking about inverses of rational functions. This is important. Your midterm's coming up, right? You're gonna have to transform functions. So you need to get this straight. Well, you have 2 basic square functions of parabola. That's a good start. Okay. But I assume everybody knows that. What's the transformation? You're thinking, okay, you're saying a shift and you're pointing to my left. But that's your right. You're saying a shift in the positive direction. Yeah. It's a horizontal shift, 3 units. Okay. So there's the transformation. You have it. You could have said it, but I wouldn't heard it. Okay. Uh-oh, we're still recording. I don't know what we're recording, what we weren't. I guess I just didn't turn it off. That's all right. Good thing nobody said anything. I guess that's why you didn't say it. You knew that we were recording. Okay. We want to graph the x minus 3 squared function by transforming the basic squaring function. I want transformation. Okay, and that means the origin, which would be in your basic squaring function 0, 0, would shift over to the point 3, 0. Vertex, which is here, is here at the point 3, 0. The point 1, 1 would shift point 2, 4 would shift here. The point -1, 1 and the point -2, 4 would shift. Our graph. I didn't quite make it down to the words, but it's a lot of real. Okay. Graph's gonna look like this. Okay. Well, we know what we did. About 6 weeks ago, about inverse functions. That we can only do the inverse of a one-to-one function. So. Function isn't one-to-one. There are y values that are associated with two different x values. It doesn't pass the horizontal line test. So we restrict the domain to the interval 3 infinity. Restricted domain consists of the x values from 3 to infinity. Unfortunately, you probably can't read that, but it's this is the restricted domain. And blue graph is y equals x minus 3 squared on the domain 3 infinity. So now we switch x and y. Our function is y equals 3 minus x squared. And if we switch it, we get x equals a quantity y minus 3 squared. Now we solve for 1. So can you solve that for 1? Okay, well, some people have it. Some people have a little bit of trouble with the algebra. So don't need to be having trouble with this algebra, but if we're having trouble with it, make sure we get it straight and understand the principles of this equation. Okay, so write it out again. Take the square root of both sides. Well, the square root of something squared is just that something. We get y minus 3 equals the square root of x. Now, among other things, well, we're just going to work. Okay. Y equals 3 plus the square root of x. Not the square root of 3. Now the other. Well, other thing is. X has to be greater than 0. Now we can see from the graph here that y on this graph is always greater than 0. So when we switch x and y, that means x is always going to be greater than or equal to 0. You're going to have to read a little bit about that and really kind of ponder. But there we have the inverse function, and then we can check. Is f inverse of f of x equals f equal x? Does f of f inverse of x equal x? Well, let's do this. Okay, f inverse. F inverse of x is 3 plus the square root of x. So f inverse of f of x equals 3 plus the square root of f of x. 3 plus the square root of x minus 3 squared, which that's what f of x is. And the square root of x minus 3 squared is just x minus 3. So 3 plus x squared is 3 plus x minus 3, which is just x, but it's 3 minus 3 is 0. And then f inverse of x equals x minus f inverse of x. Right, we're not wrong. Debating about skipping the step. I think it might not be a good idea. It might confuse somebody. And it confused me. Okay, so I wasn't thinking myself, but okay. So f of x is x minus 3 quantity squared. So this would be f inverse of x minus 3 quantity squared. And f inverse of x is three plus x minus 3, 3 plus the square root of x minus 3, quantity squared. Which is just the square of the square root of x, which is x. So both ways we ended up with x, and we've now completed the entire problem, finding the inverse and checking it. of the function x plus 3 squared. Okay. Okay, now just to repeat what I said a minute ago, inverse functions were done in the last section, of chapter 1, some time ago now. So you need to review those because, of course, you have a midterm assignment. It's you did a few of those. And I don't guarantee there's going to be an inverse function on it, but it's a likely problem. We're going to have to pick and choose problems. I made it out yet. But I hope to do that this afternoon or tomorrow. Okay. So what we just did is again, by way of review, make sure we're in shape. And we've actually done now inverses of some rational functions. We did that back when we did chapter 1. Okay, so let's do another one. Let's really review. This is a legitimate problem for the midterm. Find out the inverse of x for f of x equals 1 over x plus 7. Now, the one thing that we can do, and it's always a good idea, not necessarily required. If you have a problem, says this on the midterm, it doesn't say exactly how to do it. It doesn't say graph this function, then find its inverse. It just says find the inverse. Just leave the out. I'm going to graph it too because now we're wrapping up rational functions. We're going to do the inverses. Rational function. Okay, so we're going to find that inverse of x for this function. How do I graph 1 over x plus 7? Okay, so we want to start with this graph. As I said, it's not absolutely necessary if the problem is just stated like this, but if it has to graph it, you're going to have to do it. You have two alternatives for graphing this. First alternative somebody gave me. This. Okay, yeah, you got to shift 7 units to the left. Shift what 7 units to the left? The basic reciprocal function. This is basic reciprocal function. Horizontal shift to -7. Alternatively, here's the word asymptote, but you know, I'm talking about vertical asymptote. Long run and approaches 0 at both ends. And the y-intercept occurs when x equals 0, and that which is x is 1/7. You don't have an x-intercept. And you see that if you graph it. It's the equation because stop the equation 1 over x plus 7 equals 0. You could multiply both sides by x plus 7, but then you'd end up with 1 equals 0. Tells you there's no solution. Okay, either way, yeah. Graph is going to have vertical asymptote. And actually, it's -7. Gonna go through 0, 1, 7. So it's gotta look like this. Like this. Okay. This is as a rational function. If you want to graph it as a horizontal shifting reciprocal function, here's your reciprocal function. Here's a point 1, 1 down, here's a point -1, -1. You shift everything 7 units to the left. Well, 7 units, that's 1. Put that pretty small, we shift -7 units. It's everything -7 units, including your y-axis. When we get the graph. Not doing this very accurately, but there it is. Okay. So you should be familiar with both ways. Now, that's not the algebra we're solving it, that's what we'll talk about next. Algebraically. So first of all, this is 1-to-1. One of the reasons to graph it is we see that it's 1-to-1, we see why it's 1-to-1. That actually is 1-to-1. So we switch X and Y. So that y equals 1/x plus 7 becomes x equals 1/y plus 7. Multiply both sides by y plus 7. And this, if we multiply numerators and denominators, gives us y plus 7/y plus 7, which is 1. So we get y plus 7 times x equals 1. We don't want x over here with y, so we're going to divide both sides by x. Which gives us y plus 7 equals 1/x. So that y equals 1/x minus 7. Our inverse function is 1/x minus 7. Now don't forget the step checking this. In first place, we can graph this, and this is not a simple transformation of a basic Full-Kit function. Okay, so you have to graph this as a rational function. And if we do, we see it has a 0 at x equals -4. A vertical asymptote and x equals 2. And the y-intercept is actually at 0 and negative. Also has a slant asymptote. And I'm not going to compute that, we do a long division, related and so forth. And then the long run behavior, which is, that in the long run, X approach is Y. That's a slide out. Okay. So there's our graph. There's a function. We've got these points, we've got this half in front of the graph. Do this and up here. Do this. Okay. So the graph helps us. The function is 1, 1. We don't have to worry about restricting the domain like we did with the x minus h squared function. Okay, so switch x and y. I'm not going to write out all of the details of this one. This will be y plus x plus 4 or x minus 2. If we write that out, then we're going to get x equals y plus 4 over y minus 2. We solve for y. This is a little tricky. We've done it, but it's worth seeing again. We have done it for those numbers. Skipping some steps. Multiply both sides by y minus 2, and we end up with this. And we also have to say, well, y can't equal 2 because we can't multiply by 0. But if y was 2, we can multiply by 0. Okay. Now things get a little more complicated than they were last time. We've got y's mixed up with x's over here, and we've got a y over here. So we're going to have to use a distributive law. And now we still got an x mixed up with y, but let's get all our y's onto this side and all of our x's that we can onto the other side. And we get add 2x to both sides to get the x over here. Subtract y from both sides to get the y over here. And we end up with this. And it still looks awfully weird. Matter of fact, the first time I saw it, I thought it was awfully weird, and that puzzled over for a while. I'm not sure I had to get somebody to show me. Looked up an example of what, but that kind of like it. But the background's a little tricky, which is for most people in these courses. People get used to this. What do? You factor out one. Xy minus y is y times x minus 1. We can verify that. We just need the distributive law afterwards to get this. And now we can divide both sides by x minus 1. And we get this. Then verifying it gets pretty hairy because you got to substitute this for x in here and simplify a pretty involved function. I will ask you to do that if we have a function of this nature. But verification might be 3 points out of 10 on the problem. And you can't verify it. Makes it a lot harder to make an A. Where you're going to be. But if you're working towards C, just adequate grade of the course, and C is not a bad grade. Not being able to simplify that mess probably isn't going to hurt. Okay, hurt your chances of making A or B. So you can approach it that way. Now, we've done this. You're gonna have to review it if you want to see it, because we're not gonna do it again. Because there's something else we gotta do with the town. That has been worked out in detail. Back when we first did it, chapter 1. And probably maybe 6. I don't know. All right. A little bit about interpretation. Y equals 1,000 times 1.04 to the T. Y is the value for each of time. Okay. Now let me. What I should have. Write that Y equals F of T equals this. What's the meaning? Of the inverse function. Okay. I'm not sure I like that notation. Oh, that's right. I'm gonna just call this F inverse of X. There's no X here, there's no X here. X is just. Okay. Question then is, what would X represent? If this is the inverse function. Well, to get the inverse function, we would switch T and Y. Now, you don't know how to do the algebra of switching this. We're not going to actually try to calculate this. It turns out that the inverse function is a logarithm. And we're going to learn about logarithms starting maybe next week. Start learning about logarithms. Okay. But all the logarithm is the inverse of an exponential function. Okay. So the Y equals 2 to the X has an inverse. We graphed it. I even told you, but that's what we expected, or even tell you. I said they don't expect it to remember, but I said that that's the basic logarithmic function. The inverse of your 2 to the X function is your basic logarithmic function based 2 logarithmic function. I'm just saying those words, so they start after when we do that. So we'll do it next week. They will be new and right. Okay. Okay. Simple idea. But okay. What does F represent? What does F inverse act on? Okay. F inverse switch T and Y, right? So Y is the value, T is the time. Okay, delta T was value, T was time. Now F inverse of X. It's not the value, it's the time. So F inverse of X is time and X is value. If the value is $3,000, 3,000. What is time? X is the value, that's $3,000. F inverse of $3,000 is your time. On the graph. Remember, we had 1,000 here. Out here in the previous problem, the 1.04 to the T problem. Had 1836. So we could construct an approximate graph that indicate what we're up to. We could estimate where we get 3,000, maybe at T equals 20. Remember what we did before, and it's pretty similar what we did here. Okay, if I want to do the inverse function. Over here. X is my value, T is going to be the time, and I switch the coordinates of all these points. Okay, so 0, 1,000 becomes 1,000, 0. So this point becomes this point. Point 18, 2,000 becomes 2018. in the point. $36,000 $4,000. Becomes 4,036. Be out here a little further. Okay. This is the graph of that index. And we can see if I want to know when the value is 3,000, 4,000 down here. Actually, this 3,000 would be maybe here. And we could estimate the time. Now, we wouldn't go to this trouble if we use an estimate. We can use estimates as well on this graph as we can on this graph. But ultimately, we want a formula for this function. And the formula is going to say, you plug in the value you want, it's going to give you the time. And that's going to be very convenient. If you know what the interest rate is and so forth, you can set up your function. You can find your inverse function very easily because there's some very easy rules for finding a logarithmic function if you know the exponential function. Okay, just a couple more rules people usually don't have any trouble with if they do the work. Not nearly as difficult as some of the algebra that we've just been through with the rational functions. Okay. So things actually get a little bit easier if you focus on the rules. So people typically have much less trouble with exponential functions than with the rational functions. Okay. And they're really neat. They're very powerful. A lot of important stuff. So got that to look forward to, but the thing you really have to look forward to is your midterm. And maybe the major quiz if you haven't taken it yet.